Meanwhile, can someone let me know that am I audible and visible to you? And is the screen is visible?
Yes, it's visible.
Yeah, okay. Great, thank you. Okay, it's a time. It's 2 is to 59, only 1 minute left. So, before we start, let me introduce myself. I am Vikas Kumar Mishra and I am the TA in this particular course. So, all the kind of discussion that interaction you want to do, you can have with me one by one. What is the need of this particular doubt solving session is that there is a two aim for this to take place. First is that whatever content you have learned in the lecture, let us say week one content, which we just had in this week. If you have any doubt in that, because you cannot have interaction with the professor directly, right? Because there is only one-sided video. So in order to have some, if you have some any doubt, then you can discuss with me in this particular doubt solving session. The next aim is that if in while solving the assignment, if you, we will face some issues, so we can address all those issues. We can discuss those things, and we'll solve few questions in this particular session, which will help us to solve the assignments question. So you shouldn't face any much difficulty in solving the assignment questions, and that's the reason why that we are conducting this particular dot solving session. What I will do in every session, I will ask you, I will show you the content that has been covered, and then I will ask you that whether you are having any doubt in that or not. If there is any, then we will discuss that. If not, if the discussion is over, then we can go to the next solving the questions. Okay, which I have already prepared. So the question which I have prepared is will be mostly somewhat similar to the what you will usually see in the dot solving session. Sorry, you will see in the assignment question. Okay, so with that, let me introduce you with the portal. The portal is somewhat something like this. Here we can see that the week one content has out. There is a couple of lectures and the assignments are there. I have already solved the assignment and I submitted also, just to know that what are the questions are available. You will see that along with the week one, later on like next week, a new portal, a new box will be added over here, which will take you to the recording of this particular doubt solving session. You can go through it. Also, the question which we are going to discuss today, the PPT of that will be uploaded in that particular link. So right now it's not available because today is the first session right now. Okay, so it will be very soon. It will be available to you. Okay, so now let's get started. Okay, so the list of the content that we have covered in this particular week are as follow. Uh, can you bring me the few blank paper? So, in overview, we have seen that what and all the things that we are going to do in this particular lectures, like in this particular course. That's the overview we have seen. Also, like in the week 1 to 12, there is total 12 week. In that things, in those week, what and all we are going to do, that we have addressed over here. Next, we studied about the crystal geometry. Then unit cell, the classification of the lattice. We have classified, okay, uh, how we can classify 7 crystal system, 14 Bravell lattice, those things we have done. Then we have found that there is some gap in the Bravell lattice, right? For example, in the cubic, there is a end center is not present. For tetragonal, there is a face center is not there, end center is not there. What was the reason for that? Those gap has been addressed. We found that okay, there is a reason that symmetry is the one which is contributing toward all these particular gaps, which is happening. Okay, for example, that we got to know that end-centered cubic doesn't exist. Why? The reason is that it will transform. It will transform to the tetragonal primitive. Okay, and the reason was that symmetry, end-center, end-center cubic doesn't hold the symmetry of threefold, and that's the reason why the transformation take place. We are not so we don't write end-center for the cubic one. And then we have classified the based on the symmetry, like 4 3 fold for the cubic. Then for the tetragonal we got it, okay, there is a 1 4 fold should be there. So all that classification has been there. Then at the end we have discussed about the symmetry based approach for the Babel lattice. So on an average we have discussed some basic content of the crystallography over here. So before we move to the questions, I would like to ask you that in this particular content, do you have any doubt? If there is any, please let me know. You can interact with me in two manner. One, you can write your question in the chat box. Other, you can unmute yourself and you can have a direct interaction. Okay. Since there is no doubt, let's move to the question number one. I would suggest you all to please respond to these particular questions that we are going to discuss. Let's read what it's saying, that which of the following statement is correct. So first one is that lattice tell us how to repeat, motive tell us what to repeat. B is telling that motive tell us how to repeat and lattice tell us what to repeat. Third point is both lattice and motive are the physical object, is it? And the D is saying that okay, lattice and motive cannot exist together. So what do you guys think? Among all these four options, which one is the correct option?
Option A.
Option A is the correct option. That's right. So here we can see that okay, lattice is the one which is tell how to repeat, like something we are repeating. Let us say these lattice points are repeated. They are telling that the pattern in which, the symmetry in which they are repeating, the periodicity is telling about. While the motive is the one, like let us say we are repeating a box. So this is a motive, and while the pattern is a lattice. In the lecture, sir, Rajesh Prasad sir, he gave us the example of the heart, where he repeated the pattern onto the lattice. He repeated the heart, and in that case, we can say that the heart is a motive, and the pattern in which he is repeating is a lattice. So that's how the question moves. Is there any doubt in this question? Okay. Since there is no, let's move to the next question. Question number two. Everyone, you guys can write your answer in the comment box. Okay. A, B, C, or D. Okay. What does motive represent in the crystal structure? E. The underlying periodicity of the lattice. The atom or the group of atoms that being repeated. A three-dimensional arrangement of the points. Or none of the above.
Sir, option B.
Option B. Ah, that's right. In the comment also there is a. Rishikesh. Yeah, that's right. Perfect. So option B is the right answer. It's telling that okay, but it's an atom or the group of atom that is being repeating. Okay. So we need to also understand that it's not only one single atom. It can be like the entire molecule. It can be like even 10 to 12 atom can be associated with the one lattice point. So that entire thing will repeat. Okay. So just now I told you about the this cube, so the square which is being repeated. Instead of this square, we can have the atoms at each corner of this square, and those are the one which are repeating, or the molecules. So with that, the we can say that the option B is the right answer over here. Okay. I hope there is no doubt. If there is any, please let me know. Meanwhile, let's move to the next question. Here is a question number 3. We have to do match the following. List of things are there in the A and the B. We have to match accordingly. Okay. A primitive unit cell will match with which of this? A primitive unit cell, we know that it is something which will be having the only the atoms at the corner of the unit cell, right? That is only one atom will be associated. Sorry, that is only one lattice point will be associated with the primitive unit cell. Okay. Mrityunjay is telling that is option E at the corner. Okay, that's right. Perfect. Right, Mrityunjay. So it will be option one will match with E. Okay. Okay. Nilapur Rupas Sri. Okay, that's great. So both of you are right. What about the second option? Second, non-primitive unit cell. A, B, C, or D. E is already over, so we know no need to bother of it. The non-primitive unit cell, we know that something which will have a lattice point at the corner.
Sir, C.
Option C.
Option C. The lattice point at the corner, edge, or at the center. That's right. Perfect. So the option C is the right answer. What? How do we define the lattice translation? So among that A, B, and D, which one will be the right answer?
Option B.
Option B, Abhishek. Yeah, that's right. So we can say that if we have the multiple lattice points over here, so any lattice point, if we connect from one to another, it will tell us about the lattice translation. That is nothing but a lattice translation. So vector connecting two lattice point is a lattice translation. That is option B. Motive, we have already discussed that it can be atom or the group of atom, right? So fourth one is already over. We have discussed this in the question number 1 and question number 2 also. So the 4 will match with the option A. What about the lattice parameter? So option A is over, and we know that okay, what is left? Lattice parameter are nothing but the length and the angle of the unit cell. The left one is there. Okay, please let me know if there is any doubt in this question. Match the pair. So if we go with the sequence, A is E, first one is matching with the E, then C, then B, and then A and D. So these are the answers. Since there is no doubt, let's move to the next question. You will find the similar type of question in the assignments. How many lattice parameters are required to define the 3D unit cell? We are not talking about the square, we are talking about, let's say, cube, parallelepiped. So what do you think? How many lattice parameters are
Sir,
required?
C.
Uh, Option C, right? That's right. Yeah, perfect. So we need total 3 lengths, A, B, and C, and the angle between them. Angle between A and B will be gamma, B and C will be alpha, and A and C will be beta. So these three things are required. Okay. While in the basis form we can write that, the vector form we can write A, B, and C vector. Since so I can also write that okay, how many vectors are required to define the lattice parameters. So in that case we will write these three. These are them. If I am writing in the vector form, because they are also carrying the information of direction itself. So with that, we can say that the three length and three angles are required for the lattice parameter in the three dimension. In the two dimension, we know that we will require only two length and the two angles. Okay. So with that, we have solved the question number 5. Let's move ahead. Now, this is little interesting. How many Bravell lattice belong to the orthorhombic crystal system? We know there are the 14 Bravell lattice. Among that, for the orthorhombic crystal system, okay,
Option B.
okay, Sunava and the Rishikesh, right? Perfect. The option B. So the orthorhombic crystal is the one which is very rich among all the seven crystal system. Okay, so it is having the primitive, body centered, face centered, and end centered also. Okay, so with that we can see that this is the only one which is having all four of them. And what about cubic? Among this A, B, C, and D, if I am asking for the cubic, what will be the correct answer? Yeah, Rishikesh, that's right. Option C. Right, perfect. So in that case, we will be having the primitive, body centered, and face centered. Okay, let's move ahead. Let's go to the next question. So now this is something which we can discuss in detail. Why is there no S centered lattice in the Bevel lattice? What do you think? Why we are not having the end centered? No S centered lattice among A, B, and C. S centered means oh sorry, I think I by mistakenly pronounced the end center in between. I mean only the S center. Okay, okay. All of you are saying that the point option B, the points are not translationally equivalent. That's right. So we know that, yeah. So we know that for any crystal lattice, uh, for lattice to be translationally, lattice must be translationally equivalent, or else it will not be the crystallograph. It will not be. It will not form a lattice itself. So for example over here, just as we saw in the, let's put some edge. On the edge we are putting the atoms, and at the corner also we are having the atoms. So here we can see that, okay, translational equivalent means, okay, you all admit, translational equivalent mean that I am going here by the distance of a by 2 in this direction. So for this point also I have to go by the a by 2, and I should find the atom because I found over here. But doing the same operation, symmetry operation, I am not getting anything. Okay, I did this lattice translation, I am not got. So it is not translationally equivalent. So that's why we cannot say, we will say that n centered is not the part of the 7 crystal system, sorry, 14 level lattice. So with that, the option B is the right answer. Okay, if there is any doubt, please let me know. If not, we'll move to the next question. Huh. Which crystal system does not include a face centered lattice? Okay. So among this, which of them is not having the face centered lattice? There can be more than one answer also. C and D, Rishikesh. Yeah, that's right. C and D. Okay, let's. I think I admitted all of them. Yeah. Okay. So orthorhombic is having the primitive, body centered, face centered, and end centered also. Cubic is having primitive, body centered, and face centered. Tetragonal is having the primitive and body centered. Monoclinic is having the primitive, and we know it having the end centered. So the face centered is missing over here in these two cases, and that's how the answer C and D is the right answer for us. With that, we have solved the question number 7. If there is any doubt, please let me know. So you can see that right now the questions are quite easy, very, like within a second we can solve it. Which crystal system does not include the face centered? Okay, I already asked this question. Okay, repeated. Let's go to the next question. Yeah, so everyone please respond in the text that we have to match with that the cubic body center. Okay, okay. For those who forget that P is a primitive, C we know end centered, F we know is the face centered, and I we know is the body centered. Now let's ask for the first one, for the cubic. Which one will be the right answer for this? Cubic body centered. Abhishek is telling that it's option B, lattice point at the corner and at the body center. That's right, yeah. The one will match with the B. So in the BCC we know that there will be an atoms at the corner of the cube corner and also will be at the body center. Now about the second one, orthorhombic F, where it will be. Rishikesh, yeah, exactly right. It is option A. So the second one will match with the A. So we are done with B and A. Now about 3, monoclinic cubic. Sorry, monoclinic end center. Option D, the lattice point at the corner and the one pair of the parallel. That's right, perfect. Option D is the right answer. And then Mrityunjaya. Okay, the option D, yeah, perfectly right. So we are done with this one, and the fourth one will be lattice point only at the corner. We know that the tetragonal primitive only at the corner. That's option C. So that's how we have got that the B, C, D, B, A, D, and C. It was quite easy. Let's move to the next question. Now it's interesting little. Now let's do it in sequence. Now we have to fill in the blanks here. There are total of dash Breve lattice and dash crystal system. It's very easy. Anyone can answer it, right? So what do you think? 14 and 7. That's right. Yeah. So there are the 14 Breve lattice and 7 crystal system. The first one is over. Yeah, everyone. Yeah, that's great. Now let's move to the next question. That is a lattice with a point at the corner and the center of all faces is called a dash lattice. They are the atom FCC. Yeah. That is a face centered. That's right. So I can represent it. It's like F face centered lattice. Okay, all are admitted. Yeah. So with that, we have solved the question number B. Second, and let's move to the next one. The dash crystal system has only one Breve lattice, which is primitive. Now, what will be the answer? The dash crystal system has only one Breve lattice, which is primitive. Yeah, trigonal. But is there any other? Trigonal is there. Yeah, hexagonal is also there. So we are having the trigonal and hexagonal. Trigonal and hexagonal. Yeah. Or triclinic is also there. That's right. Perfect. So, so if we see that all of them are having the primitive, while the cubic is having the face centered also and the body centered also. Tetragonal is having the body centered only, And orthorhombic is having the body centered, face centered, and end centered. Monoclinic is the one which is having the end centered. So only
Trigonal and orthorhombic are same, I think.
trigonal. Okay,
Trigonal is
yeah,
also known
orthorhombic.
as
Yeah,
orthorhombic.
yeah. So trigonal and hexagonal and triclinic they are same.
Only hexagonal and triclinic will be the answer of this question.
Uh, trigonal is also will be there. See, orthorhombic it is. So we know that seven crystal system is consisting of the cubic we are having. We are having the then we are having tetragonal. Then we are having the hexagonal also.
Hmm.
Then we are having trigonal and which is
Which
also
is
known as orthorhombic.
orthorhombic. Yes, that's what I'm telling.
And then after that we are having the I think
Monoclinic and triclinic.
no orthorhombic no it is rhombohedral.
Okay. Rhombohedral.
And then after that we are having the orthorhombic. So we can say that the trigonal will be the one which is also known as rhombohedral. Yeah, that's Rishikesh is right. Yeah, not orthorhombic. It's a rhombohedral. Perfect. And so with that we can say that hexagonal is the right answer, trigonal is the right answer, and triclinic is the right answer. So we are having total of three answers here. So that for option C we can write the three things. Okay. Okay. Let's go to the next question. That the orthorhombic the orthorhombic system has that Bravais lattice including primitive, body centered, face centered, and that has dash Bravais lattice. So how many it is having? Orthorhombic has dash Bravais lattice. The number we have to write here.
Four, sir.
Yeah, four. That's right. Perfect. And we know that the it is including the primitive, body centered, face centered, and end centered. Okay, let me admit. Yeah, perfect. And we can here write that the end center. Now the last one. In a dash lattice, lattice points are only at the corner of the unit cell. Primitive. That's right, Rishikesh. So here it's a primitive. So with that we have solved this question, question number 10. Is there any doubt in this particular question? Please let me know. There was little confusion over here. The only thing that we missed that the trigonal and the rhombohedral they are the same name. So with that we have solved this question. If there is any doubt, please let me know. Okay, since there is no, let's move to the next question. Yeah.
Sir, can we come back to the previous question?
Yes, sir. Yeah.
Can
Sorry, Abhishek, can you repeat it? You're not audible.
in the C part, sir,
Yeah, over here.
can you please clarify that again?
Okay, yeah, sure. So, let me unshare my screen and I will share you the content. So see here, if I zoom it little bit more, this is from the lecture which we this week lecture. So here we can see that our question C was telling that the we need to find the Brava lattice which is primitive. Okay, the crystal system we have to find the list of the crystal system in which there is only one Brava lattice is there, and that is primitive. Okay, but here we can see, okay, primitive is there, body center is also there, so we'll not include that, we'll not answer this. We only want primitive. So primitive is only there in the hexagonal, it's a trigonal, and then the triclinic. Just one more thing, trigonal is also known as rhombohedral. Okay, the name was little confusion for us, but it's clear. So we can see that the only three things, that is hexagonal, trigonal and triclinic, are the one which are having the primitive in itself, and only one, sorry, primitive Brava lattice, and the only one. They're not having the body centered, face centered or end centered. Is it clear, Abhishek?
Yes, yes, sir, clear.
Okay, yeah, that's
Sorry
great.
for the
No, no, and for that only we are here. Okay, let's start. Uh, Stop presenting. Okay, admit. Yeah, so let's go to the next question, question number 11. Huh. So question number 11 is telling that why is the end-centered cubic lattice, that is cubic C, absent from the Brava lattice list? So what is the reason that end-centered cubic lattice is not there? Cubic is having only the primitive, body-centered and face-centered, while the end-centered is absent. Now we have to write the reason. It is not a lattice. It can be reclassified as a primitive tetragonal lattice. It does not have lattice point at the corner. It has a larger unit volume compared to the face-centered cubic. What do you think? What might be the reason? So the question is that, okay, let me draw a cube first. At the cube corner we are having the atoms, sorry, lattice point. And also they are telling that the cubic C means that along the C axis, so I always take this to be the Z axis. So along the C, there is
So
an
the possible reason could be fourth one, sir.
possible reason could be the fourth one. It has a larger unit cell volume compared to the face centered. Okay, let's see. We'll clarify that. Now, if we draw one more tube over here, I'm very bad in drawing, but let me try. Yeah. So here we can see that if I take this particular section, the cube is converting to the tetragonal. This is what we have learned in the class, right? Because we know that this distance and this distance are equal. They both are equal with each other, while the C axis is larger. So we found that the cubic C is being converted to the primitive tetragonal. And we let it undergo to the tetragonal. The reason we know that, if I see the cubic C, we know that the symmetry, what kind of symmetry a cube should have? Can anyone tell me? What is the defining?
Fourfold symmetry, sir.
A fourfold symmetry is one symmetry. But we know that there is one
Three
defined
fourfold symmetry.
three-fold. Three-fourfold. There is a three-fourfold is there in the cube, but the more defining symmetry for the cube is that four-threefold. Threefold is the one which is passing through the body diagonal over here, like this. So if I rotate a cube about this axis by 120, threefold means that we have to rotate by 360 by 3, that is nothing but 120. So along the body diagonal we have to rotate by 120. So what will happen that the top will come to the front face and the side will come to the top. They will rotate like this. We know symmetry operations are those which will not change, like the initial state and the final state should remain as it is. They should remain same. Now consider that we are having that the end centered over here. So what will happen if I rotate by 120? This front face, this atom will come to the front. Sorry, this top face atom will come to the front face. I'm I'm telling the atom it's the lattice point. Okay. So from top face lattice point will come to the front face, and now the entire thing has changed because nothing was there at the front face. Now something is there. The lattice point is coming to the front face. So the initial and the final are not same, and that's the reason why, since the symmetry of 4 3 fold is not satisfied here, that's why we are converted. It's able to convert from cubic to tetragonal, right? So see, among this we can say that the don't consider this larger volume. We don't focus on the geometry, like the size of the lattice. Okay, our aim is the symmetry. Entire crystallography is based on the symmetry. It is not a lattice. No, we know that it's a lattice. Which one was not the lattice? That was the edge centered. We have just found that, okay, since the edge, it will not classify among the translation symmetry. It will not satisfy the translation symmetry. So that is not a lattice. But here it will satisfy the translation symmetry. So this is also not the right answer. It does not have the lattice point at the corner. It is having the lattice point at the corner, and that is not the thing for us to even concern that. Okay, the only thing is that it can be reclassified as a primitive tetragonal lattice. Okay, so we just now we have saw that the end center has converted to the primitive tetragonal, and that's the right reason, option B. So answer B, option B is the right answer. If there is any doubt, please let me know. We'll discuss in even more detail. If it is clear, let me know. Okay. Since there is no doubt, let's move to the next question, question number 12. Guys, if there is any doubt, please let me know. Okay, no need to hesitate. You can always type in the chat box, or you can also unmute yourself and interact with me. This doubt solving session is basically for you guys to ask a doubt, to get it clear. Okay. Okay, let's move to the question number 12. If there is no doubt, what is the primary basis for the classification of the Breve lattice? Now this is the question which we were discussing. Like, what is the primary basis? On what basis we will classify the Breve lattice? Can you please explain the previous ones again? Okay, Abhishek is telling that the option B. Okay, that's right, Abhishek. But since there is some doubt in the last question, let's move to that. So right now, let's complete this question. Okay. So we got to know that for the Breve lattice classification, the primary basis is nothing is a symmetry. It's not the cell volume, it's not the unit cell shape, it's not the number of lattice points. The main thing is that the lattice symmetry. Now this will we can correlate with the question number 11. So the thing is that, let's take a fresh page. So our question was, we had the cubic end centered, and the question was that why end centered is not there in the Breve lattice. That is, it's only having the primitive for the cubic. It's only having the primitive, it's having the body center, it's having the face center, but the end centered is not there. Now the reason we wanted to know. So if we draw a cube, I will just explain the same thing but little bit slow pace. we are having the atom at the corner. Now if since it is cubic, sorry, since it is n-centered, that is along the C also, so it is, we will place an atom or a lattice point over here also. Now the reason why it's not existing, we know it's not existing. Let's draw one more. Let's extend the unit cell. Like, in order to understand why it is not existing, we'll extend the unit cell. We'll see that whether the n-centered cubic is converting to some other symmetry, some other Bravais lattice or not. So again we'll just repeat that, okay, the list of atoms we are having or lattice point we are having, again at the top and at the bottom we'll have. Now if we see that we can make a unit cell of this shape from here. And we can connect them. Okay, so what this particular shape, this shape is nothing but a tetragonal, right? Because this length and this length are equal with each other, and this length is quite high, that is, this entire length is a, if we consider the lattice parameter to be the a, and this will be the a by root 2, this length, right? So, and this things will be 90 degree, all of them are 90 degree. So we got to know that here, if we consider this unit cell, this new unit cell here, let me call it the a dash because I am calling this to be the a dash is equals to the b dash is not equal to the c dash, right? So this is my c, this is my a and b. A dash and b dash are a by root 2 and c dash is c, and all the angles are 90 degree. So we can classify that, okay, this has converted to the tetragonal. But just by this I can convert anything, even the face centered also we can convert to the tetragonal, like the face centered cubic. If we keep on doing in this way, we can convert anything. But now you can argue that, okay, why don't we remove the primitive tetragonal and keep this, right? Now there is a competition, right, that the primitive tetragonal it is converting. Cubic C converted to the primitive tetragonal. So while in the Bravais lattice we are only keeping this, we are not keeping this. Now the reason for that why we are keeping is that in the cubic we know there is a fourth threefold. That is a threefold is there. Threefold mean that the threefold rotation should satisfy. Now let's consider again the one cube over here. There are the atom at the corners, sorry, lattice point at the corners and at the end center. This is our initial. We can name the top one as the top face. This will be the side face, let us say. This is the one which we are having, the one which is facing toward us. This one I'm talking about. This is the front face. Now about this particular axis, body diagonal, I am rotating it by 120 degree. So now what will happen? This faces will change. Top will come to the first, front, side will go to the top, like this. They will interchange. Now let's see what will happen at the end. All the corner atom will be there, Now what will happen? This top lattice point will come to the front lattice point, while the side one and this front will go to the side. Nothing is there on the front also. It won't be here. Side will go to the up. So we can see that okay, this was the side one, this is the top face, and this was the front face. They interchange each other, all of them. Now what do you think? This initial state and this is a final state. Okay, the initial state, we can see that at the top we were having the atom. Here at the top we are not having atom or lattice point. Here in the front we were not having the lattice point. Here we are having the lattice point. So here threefold, which was the defining symmetry for the cubic, is not satisfied. We are rotating by threefold. It should happen that okay, they should satisfy with each other. They should equal with each other. So since the threefold is not the symmetry operation over here, so this is not a cube. This is not belong to the cubic system. Okay, you can tell that okay, a equal to b equal to c, alpha equal to beta equal to gamma equal to 90 degree. Still, it is not the cubic. The reason is only that we are having the symmetry is not satisfied. The most important thing is that symmetry is satisfied. Now let us say I converted to the tetragonal. What is the defining symmetry for the tetragonal? Can anyone tell me? The defining symmetry for the tetragonal, it is a fourfold, right? It is a fourfold along the c axis. This is the c axis. So now let's consider this, the thing which we have made. So here, this one and this one, we can place them over, okay, somewhere over here. So all at all four corners we were having the one lattice point. All four corners we are having the lattice point. Let's put them. Now about this, rotate by 90 degree. This one will rotate to over here. This one will rotate to over here. This one will rotate to over here. Symmetry will be satisfied. The initial and the final state will remain as is it. They will remain same, and that's why we can say that this structure, the cubic C, is not satisfying the cubic, that is threefold symmetry. It is satisfying the fourfold symmetry of the tetragonal, and that's the reason why we converted it from cubic to tetragonal primitive. Right? Please let me know, is it clear? If there is any doubt, you can please unmute yourself and interact with me. Okay, clear. That's great. Okay. So now let's move ahead.
Sorry, it has fourfold symmetry on and c axis. What about the other two axes? The A and B, it can be twofold symmetry, right?
Sorry, can you please repeat again?
Yeah, about c axis, the tetragonal lattice having the fourfold symmetry, right, sir?
Yeah.
So
Yeah.
what about A and B axis? Like what about other axis? It has only twofold symmetry.
Other are having the twofold symmetry only. So in the tetragonal, that's why we said there is a one fourfold symmetry. Only one fourfold symmetry is there. Okay. While in the other
Okay, sir. Thank you.
along other axis, it's only the twofold symmetries are there. Right.
Yes, sir. Clear, sir. Thank you.
Yeah. Okay, so we have solved this question number 12. So we will keep in mind, we will always keep in mind that the the basis for the classification of the Bravell lattice is not the shape, is not the size, it's the symmetry. Okay. So question number 12 is over. Let's move to the next question. Okay, I'm having a lot of questions. Now since we are following, who we are doing all these questions, like these questions we are already answered. So now let's just see that is it in our mind or not. Like, what is the defining symmetry of a lattice? What is the defining symmetry of the lattice? Whether a particular lattice is will exist or not. What is it? What defines the lattice to occur? Is it rotational symmetry, translation symmetry, point symmetry, or reflective symmetry? Anyone?
Rotational symmetry.
For the lattice, I'm talking about. See, a lattice. Option C, point symmetry. Okay. Nilapur,
B, translation.
yeah, yeah, that's right. C is translation. See, we know that just now we few moment back we discussed that for any lattice they should satisfy a translation, right? Let us say I'm going from here to this point. Same lattice vector, if I draw from some other lattice point, if I move by the same distance of a, let us say, I should encounter another lattice point. That is the most important thing for the any lattice to exist. Okay, so you can see in this particular way also, like let us say I am moving from here to this particular lattice point, this translation vector. Now I can start from here also. If I move in the same direction by the same magnitude, I should encounter another point. Okay, this is how we can define that the something is lattice is existing or not. It should only it must have the translation symmetry. If there is a translation symmetry, then we can talk remaining things and all. But if translation symmetry itself is not there, there is no point in further interaction that okay, whether it's cubic, tetragonal, and what so on and so forth. The first thing a lattice should satisfy the translation symmetry. Okay, so with that, that's how we have solved the question number 30. Yeah, please let me know if there is any doubt. Let me address these things. Rotation symmetries are has been noted over here. Point symmetry and the reflective symmetry. Reflective symmetry is what? A mirror, right? Mirror symmetry. Rotational, we know that okay, number of folds, one fold, two fold, three fold, six fold, those things. Point symmetry are the collection of these particular things. That is a mirror, a rotation, and inversion. So I have rotation, mirror, and then I have inversion. Combining entirely this thing, they will form the point symmetry. These are just information because these words are used here, so I am telling you. Now this information will be useful to answer the further question which we are going to face. Okay. Now if I add a translation to also it, if I add translation, see, three symmetry operation, rotation, mirror, and inversion. If I add translation, this entirely will form a space group. Point symmetry, now this will form the space symmetry. That's how we have solved the question number 3. So, and these are the information that we are going to remember, which are going to help in solving the further questions. If there is any doubt, please feel free to ask me. If not, let's move to the next question. What is the minimum angle of rotation for the four-fold rotation symmetry axis? Okay, they are telling that with four-fold. Okay, what do you think? Which will be the right answer? A, B, or C?
90 degrees.
90 degree, right? That's right answer. So if the nature, let's say n-fold is given to us, how will we find it? Whether by what angle it is rotating? Divide
So 360 by n, sir.
Yeah, that's right. Perfect. 360 by n. So whatever we are getting the value over here, that will be the theta will be considered. So in this case, we are having the four-fold. So we will divide 360 by 4, and we will get that it's 90. For the two-fold, we will divide it by 2 and we'll get 180. Okay, we know in the two-fold that we will rotate by 180 degree. Uh, Now, for the cube, I told you that it's a threefold. So for the threefold, what will be the value we will get? Okay, admit. So for the threefold, what will be the rotation angle?
120.
120, right?
120 degree.
Yeah, that's right. Perfect. So with that, we have solved this particular question. Question number 40. If there will be any doubt, please let me know. Yeah, that's right. 120 degree. Now, according to the crystallographic restriction theorem, which of the following rotation symmetry is not allowed? Remember, which is not allowed over here in the crystal. So
Five-fold symmetry.
yeah, it's a five-fold, right? Yeah, the five-fold is not allowed. So option B is not allowed. So what are the allowed symmetry? One-fold, two-fold, three-fold, four-fold, and six-fold. Corresponding angle is 360 degree, 180 degree, 120, 90, and 60. So these are the allowed rotation that crystallographic restriction theorem is telling, that only okay, if there is crystal, if you are talking about the crystallography, so only this five are the one which are existing. Five-fold symmetry, that is contributing the 72 degree of rotation, is not existing. Okay, so with that, the question number 15 we have solved. Any doubt, please let me know. Okay, since there is no, let's move to the next question. No, so we have discussed more, three, four things among this particular stuff. Now let's try to answer that the translation symmetry. There is option column A and column B are there to us. 1, 2, 3, and 5. So what do you think? Translation symmetry. Symmetry in a mirror plane, point map to equal distance on the other side, defining symmetry of a lattice. Abhishek, yeah. Abhishek, that's right. So we have discussed that just now, that translation symmetry is the one which is defining symmetry for the lattice. So the first one will match with the C. Yes. Now two-fold rotation symmetry. So now for two-fold, what do you
Theta
think?
minimum 180.
Yeah, that's right.
E.
Yeah, the E is the right answer over here. The second one will be the E. Now for the reflection, what do you think? A, B, or D?
A, sir.
A, right? That's right. Yeah, that's great. The option A is the right answer. So here we can match with the E. So now what about the crystallographic restriction theorem, which we just talked about? Fourth one. Which one will it match? B or D?
D, D,
D.
D.
So this is done. Now for the inversion. So now inversion, what is the inversion? Like it is about the point. Let's say we are having the, this is a x-axis, this is a y-axis. We are only talking about in the two dimension right now. I have some point which is x and y. I inverted it. Now after inversion, what will happen? It will come to this point, which will be minus x minus y. So all the coordinate will change, but the distance from the origin, distance about the point where it got inverted, will remain same. And so we can add the point map to equal distance on the other side. Other side means that opposite to the origin, opposite to the inversion point. Similarly, the way we talk about the two dimension, that is a x and y, we can also introduce the next dimension, that is z. So now here what will happen, that the x will convert to the minus x, minus y, and minus z. And in 3D we can say that again all the points will change, all the coordinates x, y, and z will change. But the thing is that about the inversion point, the distance will remain as it is. Okay, so we can, fifth one will match with the option B. Okay, so is it clear? If there is any doubt in this question, please let me know. Okay, since it's clear, let's move to the next question. Now, what is a general rule of symmetry when two orthogonal? Orthogonal, we know that it's a perpendicular mirror intersect. A, B, and C. A four-fold axis is formed, two-fold axis is formed, a reflection plane is formed. None of them. So they are telling that the two orthogonal mirror are there. Let's first of all let's get one object which is which can show these two orthogonal mirror. How about I take a rectangle? In the rectangle we can see that there is a one mirror which is this. Second mirror is horizontally. They are talking about that the general possibility when two orthogonal mirror intersect. Now they are intersecting each other. And the important thing is they are intersecting orthogonally. Now if you see that if I rotate about the center this thing by 120 degree, they will coincide with each other, right? Let's say I'm rotating this particular rectangle. What will happen? I will get the same exact same rectangle. This A, B, C and D. Let me mark. So what will happen? Max to max, what will happen? This A will come to here, B will come over here, C will come over here, and D will come over here. But the thing that they are representing the same thing, their symmetry doesn't got disturbed. So always remember, when two mirror intersect with each other orthogonally, the intersection point will generate the twofold. Okay. So along this axis, I can rotate by the 90 degree. Oh, 180 degree. It's a twofold. So we can say that the twofold is formed. So the option B is the right answer. Right? If there is any doubt in this question, let me know. See, all of these things has been discussed in the class. We are revising also with each other, and also we are solving the questions. You will find the similar type of question in the assignments. Since there is no doubt, let's move ahead. Before that, let me again show you that question which we have solved. Say we have solved this question number 13. Here what I said, that the rotation mirror and inversion will combine under the, like, they belong to the point symmetry. If I add translation also to the point symmetry, we'll get the space group, right? If I add translation to the point group, they will give to the space group. So now let's try to answer the question number 18. What is the relation between the space group and the point group? A, B, C and D. Which one will be the right answer? What do you think?
C.
That's right. That C is the right answer because both translation and the point symmetry will be present over here. So the option C is the right answer over. Right. So we can say that space group is equals to the translation symmetry plus point group plus point symmetry. Okay. Very soon we will wind things. We are left with only few couple of questions. Which crystal system has the least symmetry? No, least symmetry, it's not symmetrical. Very, you can see that we were talking about the n-fold. No? So 1, 2, 3, 4, and 6 was,
Triclinic.
yeah, triclinic. Triclinic is the one which is having the one fold symmetry, that is 360 degree, because it here none of the sides are equal, none of the angles are equal. It's a more general, and that's why we can say that it's a least symmetry. Now if I reverse the question, it's not there in this. You can consider the seven crystal system. Among that, which of the crystal system which is the most symmetric?
So mostly
Hexagonal.
hexagonals.
Sorry, there was two answers was there.
Hexagonals.
Hexagonal. See, you're talking from this, but we can see that hexagonal is having only one sixfold, while the cube is having the four threefold. It is having the four. So the cube is the one which is the highly symmetrical, is the most symmetric among the seven crystal system. Okay, so in that,
Trigonal.
uh, sorry, cubic is the one which is highly symmetrical. Uh, is there any sorry, your voice not audible. Can you please repeat again? Subrat, Subrajit. Okay. Yeah. Okay, there is some network lag, I think, on the Subrajit side. So yeah, so the cubic one is the one which is having the highest symmetry over here. Yeah, Subrajit, is there any doubt? Please let me know. Okay, since there is no, let's move to the next question. No, this is little interesting. Okay, that's great. So now we are having a triclinic, monoclinic, tetragonal, hexagonal, and cubic. One by one, we'll do all. So, what do you guys think? For the triclinic, among these, which one is the right answer? B, Abhishek. Yeah, Abhishek is right there. Option B. It's not symmetrical. It's like no special symmetry. It is only having the common symmetry which all the object in the world exist is having. Okay. If I myself rotate by for I myself rotate by 360 degree, the result will same. Right. So here we can say that the first one is matched with the B. What about the monoclinic?
Single twofold, sir.
Single twofold. That's right. Perfect. So we can say that the monoclinic will be having the option A. Tetragonal is
Single fourfold, sir.
single fourfold. That's right. Perfect. So the option E. Now about the hexagonal, we know
Single sixfold.
single sixfold. That it will be matched with the option D, and the cubic one will be matched with the. We talk a lot about this, right? So the cubic is the left one. It will match with the option C, four threefold. So the B, A, E, D, and C. These are the sequence. So we have solved the question number 20. If there is any doubt, please let me know. Here. Our next question. Which axis determine the cubicity of the lattice in the symmetry based approach? Cubicity. That is, we are talking about the cube. Okay. If something is cubic, whether it's a cubic or not, which of them will define that okay, this is a cubic? Two four, two-fold axis about the x, three-fold axis about the body diagonal, four-fold axis about the vertical, or six-fold about the c-axis. Okay, so for the cube,
Threefold axis along the body diagonal.
three-fold axis along the body diagonal, we have talked a lot about this, right? Like the way we have told that if we rotate about the body diagonal, the top face will come to the front and the front will go to the side. So about that we were talking about. So the cubicity is defined by this. So with that, we have solved this question 21. Yeah, right. Why was the unit cell of the cubic F not reduced to tetragonal I despite having a smaller volume? So they are what they are telling that okay, let's you are having the cubic F. Now this will be little complicated, just as the last thing which we have discussed, like where we were discussing about the cubic end center. It is having the similar type of explanation.
Sir, one doubt, sir. Before going that part, can we know what is F and I?
Okay, F is a face centered, I is a body centered.
Okay,
Cubic F.
sir.
Yeah. So here we know for the cube the atoms are there, sorry, the lattice points are there at the corner as well as they are there at the face, front and back also. Now they are telling that why don't you convert this to the tetragonal line, that is the body centered. So let's see. Before I explain, can anyone tell something like what do you think? Why it is not possible? Why we not did? Why we are like why the cubic F is not converted? See, the main reason which I told that it will be based on symmetry entirely. So this is also based on symmetry. But first, let's understand the question before we answer these things. Let's understand that okay, how the cubic F and tetragonal lie they are telling that they will convert. Why this question itself is arise. Okay, now again we are having that the faces and the front and the back also. So telling that okay, the way we converted cubic end center to the tetragonal, let's convert this also. Gitu, bring me this blue one somewhere. It will be there. It's almost over. I think that one is also over. This one. So they are telling that okay. Now why the body center? So this is the tetragonal. We know we have drawn it before. Now at the now this phase, this center, this lattice point is lying at the center of the tetragonal. So now they are telling that okay, you have got one tetragonal where the lattice points are there at the corners and also the lattice point are there at the center. So why don't you convert this to this? Because and also they are telling that the tetragonal is a smaller volume, right? See, we know
So
that
at side faces, we are remaining with some atoms.
uh, sorry, can you please repeat again?
Within the tetragonal after conversion, at the side faces, we are remaining with some atoms, sir.
Side faces. You're talking about this sides. See,
Yes, sir, yes, sir. So we are deriving this from that face centered cubic. Right?
face centered cubic. So within that, this face is entirely incorporated in this particular. So this lattice point will be there at the center. Now this lattice points are at the corners. So they are coming at the corner. They all are at the corner. They are coming at the corner. And there is no other phases like this phase is far away, The this back face is also the far away from this thing, so they are not. So the all the lattice point we have incorporated over here. So now cubic is not, this is a smaller dimension also compared to this. So this is the question. Now we have understood the question that why we are not doing this. This is what the question is asking, why you are not doing this. The reason we know that for any conversion to occur like this to this, a symmetry should satisfy. If symmetry is telling that okay no this is a cube, so it will remain as a cube. If symmetry is telling that no it's not a cube, convert it to something else, whatever the symmetry it's telling, then we will convert. Now let's say that, now let's find that what symmetry is telling that about this particular face centered cube. That is why it is cube. Let's draw the cube. Okay, my cube is little distorted, but okay, we can consider. So till now we have discussed multiple times that that it's a symmetry. Symmetry is the one which is contributing for the cube, and we got to know that it's a threefold. Threefold about the body diagram. Okay, about this particular axis. I am drawing the triangle. This triangle is a representation of the 120-degree rotation. So now let's draw the face centered. Like at each faces there will be an atom or the lattice. The front will be also there, and at the back will also be there. Now let us say I am rotating this. Let's call this to be the 1, this front one to be the 2, and this side one to be the 3. Now I am rotating. I am rotating about this. So this side atom, side lattice point, if I rotate by 120, it will coincide with the 1. 1 will come to this particular 2, and 2 will come to this 3. Right? So the all of them are satisfied. Like after the rotation of 120 degree, I am getting the same structure. So it will remain cube because it is satisfying the 4-3-4 symmetry of the cube. Okay. So that's how it is. While in the case of end-centered, we have saw that since there were not, this lattice points was not there, end-centered which we discussed, we saw that this was not there, only the top and the bottom one was there. If I rotate by 120 degree, it will come to the front, but nothing is there at the front. Right? Initially there was nothing at the front. So the rotation by 120 degree distorted the cube. Like the symmetry is not prevailing. Like the initial and the final is not the same. And that's why we converted end-centered to the tetragonal primitive. Here we are not converting to the tetragonal primitive because the symmetry of threefold is satisfied. Now let's answer the question. I hope this is clear. If there is any doubt, please let me know. So now why we not did? Symmetry dictate that the cubic eye must remain cubic, right? So the option B, sorry, cubic F must remain the cubic. So with that we can say that the option B is the right answer. Cubic F does not have any threefold. This is wrong. We saw that it's having the threefold. Cubic eye must be the higher symmetry than the cubic. Sorry, tetragonal having the higher symmetry than cubic. No, we know that the cubic is the most symmetrical. The one which is at the top will prevail. So it is again the wrong answer. The tetragonal eye is not a valid Bravais lattice they are telling. No, tetragonal eye, that is the body centered, is exist, but still we are not taking it. The right answer is option B. If any doubt, please let me know, or else we'll move to the next question. Guys, again I'm telling that if you face any doubt, any difficulty in this session, please let me know, because here is this is the only place where we can discuss the things. Okay. Now this is our final question, last one. What symmetry does the lattice become when the fourfold axis is lost in the tetragonal line? again similar type of question is there. Okay, we are having the tetragonal A. See, tetragonal C was quite interesting. Now let's see the tetragonal C first before we answer the tetragonal A. We know in the tetragonal there is a 1 fourfold, and this fourfold was about the C axis, that is about this particular axis. Passing through this. Now if I put C, tetragonal C, if I am talking about the tetragonal C, what will happen? That is the lattice point is at this point and this point. So now if I rotate by 90 degree, it will remain as it is, no problem. Right, it will remain all these particular points, all these points, this will rotate to this will rotate to this will rotate to this. The initial symmetry and the final symmetry will remain as it is. It's like the initial object and the final object which we will get will remain same. Now let us say, now we are talking about the tetragonal A. Tetragonal C means that this were at the C axis. A means that they will be at the A axis, along the A axis. So let us say I am considering this to be the A axis. You can consider this also. Anyone is fine. Like both of them will do the same thing. Now this was my the fourfold rotation axis. About this I was rotating by 90 degree. Now let's see, now let's rotate this by 90 degree. What will happen? This is our state 1. I am drawing one tetragonal here. This will be our state 2. I should have taken some new paper. Okay, it's fine, I think we will be able to do it over here. No. The axis will remain over here. Now what will happen? I am rotating by 90 degrees, so this will rotate, the side one will come to the front face, like the side face, this atom will come to the front face, so it will come over in this particular region, in this particular face, front, and this one will go to the back, 90 degree rotation, it will go to the back. So what we can see over here, the first state and the second state, they are not same, and they are different from each other. Here the lattice point was along this side faces, here the lattice point along the front and the back face, so they are not parallel, they are not equal with each other, and that's why the tetragonal A doesn't exist. Now so on what thing tetragonal A transform to? We know that since it doesn't exist, so what is this? We know that in the orthorhombic, what orthorhombic say that? Orthorhombic say that it is having the twofold axis along all three, right? Twofold. If I rotate this by, let us say, now consider only this. Here A is equals to B is not equal to C, and alpha is equals to beta equal to gamma equal to 90 degree. Here it is happening. Now this, if I consider this to as a, let's say it's not a tetragonal, we got to know by the symmetry that it is not satisfying the fourfold axis, fourfold symmetry. So we'll go to the lower symmetry, twofold. Let us see that will it satisfy the twofold symmetry. About this I am rotating by the twofold. Rotate it. This will come over here and this will come over here. The entire rotation will take place of 180 degree. Twofold means 180 degree rotation. So about this it will happen. And that's why even though A is equal to B equal to C and A equal to B not equal to C and alpha equal to beta equal to gamma equal to 90, even though this is satisfied, this is not a tetragonal, this is the orthorhombic, and this is what a symmetry is telling, that it's not a tetragonal, it's an orthorhombic. So we can say that it is satisfying the symmetry of the orthorhombic. And with that, the 20, we have solved this question. So, with that, we have solved all the questions that I plan to solve in this particular lecture. Now, I would like to ask you that please, if you have any doubt, feel free to discuss with me before I wind up. So one by one, I will show you the question that we have solved. Go through this, have a look onto it. If there is any problem you will face, let me know.
So can you explore?
Yeah,
Can you send this document?
yeah. Everything will be uploaded onto the, like, you want question only, or you want this the thing which we have solved also.
Explanation also, sir.
Yeah. So see, just as I told you, let me unshare my screen. So there is a weak one. There will be one more box will be added over here. A link will be added where you can see that okay, it will be consisting of the doubt solving session. It will have. You can click on that. You will find the entire recording itself, and also you will find the link of the PPT where we are like where all those questions which I discussed will be there. Okay, and the recording which we are discussing, whatever we have discussed till now, everyone can see that. Okay, everyone will be able to access to it, so there won't be any problem. Okay, yeah. So I was showing you guys a question that we discussed.
Yes, thank you, sir.
Yeah. Stop presenting. Jason to say. Okay, yeah, perfect. So in 19 we talk about the list symmetry. In the question number 18 we have talked about the both the like space group and the point group symmetry. Here we have talked about the what is the defining symmetry of the lattice. That is nothing but a translation symmetry we got to know. In this particular question we got to know that if two mirrors intersect each other orthogonally, then they will form the twofold axis. Now here we just revised the concept and we got to know that okay, there is something known as inverse symmetry is there, which will convert, which will like transform all the axes from positive to the negative or negative to the positive. Only the thing is that it will keep the distance about the inversion axis same, inversion point same. Then we talk about the crystallographic restriction theorem, and here we talk about the what about the fold of rotation, what theta is representing, what n fold is representing. Then here we talk about the Bravais lattices, like what is the basis of classification of the Bravais lattice, and we got to know that it is symmetry. Then we discuss about that particular problem in which we face a lot of difficulties in understanding that why cubic C is absent and it has converted to the tetragonal. These are the few basic questions which we have solved that all of this question you guys have answered it. Then again, this is also very basic. The crystal system. Okay, I repeated this question. So we not solved 23 question today. We solved 22 question. Next time we will aim only for the 20 question. So again on the next Saturday, on the same time, we'll have a discussion on the week 2 content. Yeah, then see here, no edge center. Why it was not there? Because the translation symmetry was not prevailed over here. So the translation symmetry is the must for the any lattice to exist. Now here, how many Bravais for the orthorhombic system? How many Bravais lattice are there? Then here we talk about some basic stuff. Nothing much here. Everything you guys answered. Everything. Yeah. So with that, we have concluded our today's discussion. Also, you can solve the assignment. If you face any difficulty in the assignments now, we can you can submit those assignment, not a problem. And there is no negative marking. And also the thing is that you can submit it multiple times. Okay. Let us say today you solve, tomorrow you are realizing no something you you put the wrong answer, again you can resubmit it. If you face any difficulty, again we can discuss the answer, like we can discuss the solution of those assignment in the next week. Okay guys, with that we can conclude our this particular session. We'll meet again in the next week.
Thank you, sir.
Yeah, okay, bye bye.
Thank you, sir.
Yeah, most welcome.